Hey, let's see. Is the quiz tomorrow gonna be on 5.4 or just 5.1 and 2 and 3?
Well, Ksenia wanted to move the quiz to Friday, so I think if we want to do it on Friday, then it's going to be on 5.4 as well.
If we do it tomorrow, it's only on 1, 2.
Correct.
Oh.
So you guys can figure out what you want. I'm open to either one. All right. So, like I was saying, we have elementary reaction. This is what we've told you all along. Hey, this is our reaction. In reality, in most cases, that's not what's actually happening. There's actually intermediate forms of the reaction. So when we look at this, we've got a net equation that is up here. That's what we've been having you balance all this time and everything like that. What we need to talk about now are these elementary steps. And then we're going to bring in what we just did where we talked about which steps are slow and which ones are the rate determining steps. So if we look at the two elementary steps of this reaction, we can see that we have this guy and this guy. The stuff here at the beginning forms this, and then that goes in, combines with the oxygen to form our final product. The things in between then that aren't part of the overall reaction, we cancel those out. Those are called, if it forms here and is used up here before the end, that's called an intermediate. Okay? So, any questions about that? Does that make sense what an intermediate is? The sum of these elementary reactions then is that overall balanced equation. That's the one that you've been working with all these years. Okay, good. You okay there, Jaden?
No, Jaden's dead. I'm like,
all right. So,
He fell like 4 times.
the molecularity of the reaction describes the number of molecules that have to collide in an elementary step. Both elementary steps are bimolecular, meaning that there's 2 molecules, as they have 2 colliding molecules. Unimolecular reactions involve only 1 particle, and those might be like a decomposition or a decay or something. Termolecular reactions then involve 3 colliding particles, but that's pretty rare because the likelihood of 3 things actually colliding simultaneously is probably not going to happen. Okay, so if you've ever tried a 3-person high five, do we need to try that? I'll try it fast. Exactly. Okay. Okay. So a 3-person high five, you try that fast enough to make the things hit together the way they need to. It's pretty hard. Okay. So that's what we mean by termolecular being rather difficult. The rate law then can be inferred from the elementary step based on the number of molecules that have to collide. For example, in this reaction that we had before, our rate law is this. As there are 2 particles of NO that have to collide, it would be second order. The rate law for step 2 then would be something like this, where you would have this guy colliding with this guy. Okay? Now, sometimes you're given information about the speed of the elementary steps. Now, this is important right here. The slowest step is known as the rate determining step. That is going to limit how fast your reaction goes. So when we did our little activity out here a few minutes ago, Who were our rate determining steps? Matthew and Jaden. They had the longest way to go. They had the most to make happen. That is going to be our rate determining step. So if we look and see what's involved there, that's going to determine how fast our reaction is going to proceed. Okay, so here, they've got an example here with a chocolate chip. It takes you 15 minutes to make chocolate, 8 hours for it to cool, and 5 minutes to box it. So which step is going to take the longest? The cooling. So that is going to be your rate determining step here. That's the step that's going to limit how fast you can make the chocolates. Speeding up, if we did this in 7 minutes and we did this in 2 minutes, it's still not going to change how long it's going to take for our chocolate, because this is going to determine our rate. Okay. So the slowest step of the reaction determines the rate of the reaction. If the first step is slow, then the overall rate for the reaction is based on it can be based on that stoichiometry. Okay. So if this is our rate determining step, this would be our stoichiometry for this. So our rate law would be rate equals K times A squared. That would be our overall rate law. Okay. But that is only if that is in the first step that we can do that. If that's not in the first step, then we have to sub in the stuff into this. Okay. So for example, here, this has B in it, right? But B is an intermediate. Do you see how B is an intermediate? So we can't put B in our rate law. We can't have that intermediate in our rate law. So we have to go back and see how B formed. B formed from 2 A's. So our rate law here would be those 2 A's to make this B, and then the C would come here. That makes sense? All right. So here, given the following elementary steps, what is the overall reaction and what is the rate law for elementary step 1? So if we look at this, we're going to get rid of our intermediates. We don't have anything called catalyst here, which we'll get into further later on. The catalyst is something that appears here and appears in the final, and they end up canceling each other out. Okay. So they said that we wanted the overall reaction, and the overall reaction should end up balancing. So the overall reaction will be 2HI yields H2 plus I2. And you can see here that I've got 2 H's. I've got 2 I's on both sides, so that does balance. They then said that this was our slow step, and they wanted the rate law. So the rate law is going to be rate equals what? HI how many? 2. I've got to have those 2 things collide together to make that happen.
Wait, I have a question.
Yeah.
So how do you know that the first equation is like the slow one? Like how do you know that that's like the first
Well,
one?
they said what is the rate law for elementary step 1. So if the rate law is determined by step 1, that has to be the slow one. They would have to tell you, or you would have to have data. You would have to have something that tells you. And in this case, that's what told us. All right. We've got this guy breaking into 2 of these in a single step unimolecular reaction. Write the balanced equation for this reaction, then write the rate law based on the stoichiometry of that elementary step. So we have C4H8. It's going to break into two C2H4s. And our overall rate law would be rate equals K and then C4H8. What is my overall reaction order for this reaction then? What? What is my overall reaction order for this reaction? 2. Second order. Good?
So this second, so the leader is a half-life.
Yeah, it would produce a perfect half-life curve if you did concentration time versus time. Concentration versus time will give you a perfect half-life curve. Okay. If you did the natural log of concentration versus time, you should end up with that.
Why did you have a K in front of this open up the other one?
I didn't have a K here because I screwed up. You gonna be all right?
Yeah.
I worked you too hard.
Jake,
Thought it was AP Chem and not Phy-Ed.
you are right.
It's like, why is there like
All right, so I think that's all I had for today. Look at the front of your packet.
Yep,
Okay.
worked it.
So you guys can vote on whether you want a quiz tomorrow or Friday.
I mean,
Okay, why don't, hey, just, it's an odd number of people here today, I believe, right?
So I get to decide.
So I'll give you a slip of paper and you can vote Thursday or Friday on there for when you want your quiz and we'll figure it out from there, okay? And then I'll let you know. So you've got time to work on 5-4. You've got time to work on your lab. I know there were some questions about the graphing with the lab. Megan has figured out how to get that thing to graph right. So if you're having trouble selecting the right columns and that sort of thing, go and talk to her. She will help you out with that, okay? And I'm voluntolding you. Sorry, Megan. But it's just the way it is. All right.
You need to send me the file.
Matthew, I am not some tech whiz. You need to help me.
Come over here and sit in your spot.
All right. So you